Yeah, I opened the door.
Yeah,
And I was like, this is insane. They had the heat on high.
yeah, they had the heat on high.
It's supposed to be 60 degrees today.
I mean,
What do we do? So
I
why
don't
are they coming
understand.
here just to vandalize it?
I feel like they just come in here and just mess things up and leave.
Like a professor that teaches a class that he's not supposed to teach.
Well, it's like, I think it's some adjunct because I've never heard of the person.
Oh, who is it?
I don't even know the name. Like, when they mentioned the name, I didn't know who that was. And I know all the English professors, like the full-time ones.
Yeah.
Anyway, I don't know, but I was unhappy. I was very unhappy.
Well,
Very
it's
happy.
day 20.
Day 20, I wish. 28. Dang, that'll be nice.
But now they only have 2 weeks left.
Only 2 weeks.
My mom said every Monday. Until 7 more weeks. 6 more weeks.
Really? Good for her.
She knows that I am so ready to just like.
Be done.
Because
Oh,
I've been like, for me, I just need like a break.
yeah,
Like, I've been so under fire with all this work, and it's like hard.
yeah,
I told her, I was like, look, I don't wanna go to graduate school right away.
yeah, I know. It takes some time.
I wanna get it, I need to figure out what exactly.
Yeah.
It's looking like it might be. I need a break from the contract and from class. Like,
I hear
I
that.
wanna work for a little bit, build up some money.
Yeah,
Have a little relaxation time.
yeah,
Holy crap.
I hear that.
Like,
Yeah,
whatever you wanna do, it's fine, as long as you have a job, like job, whatever.
yeah,
Like, it's fine. I'm like, yeah, we can never get a job.
yeah. Well, see what happens, right? You might end up just liking that, and that's what you do, you know?
Yeah, right now I'm at, Dr. Sheldon's in the situation with my job.
Mhm.
There's this, it's called the regular,
You mean nuclear,
yeah.
not nuclear? FYI,
What?
you say nuclear. Nuclear. Yeah, nuclear. There you go. You don't want to show up to the job and say it wrong.
What is it?
Nuclear. It's common, like someone started saying that in like 1995, like in the government, and then it just took over and like everybody says it wrong
Yeah,
now.
there were people who keep saying.
Yeah, but the speaker didn't say that. Yeah, nuclear. So practice it, so you don't go to the
I said nuclear.
nuclear. That's a common like mispronunciation. And if you go to the job interview, make sure that you're like nuclear. Anyway, keep going. So,
Basically, it's gonna be like the kind of homeschooling, but it's like,
yeah,
they'll send me to like a certificate. Essentially, it's technically an associate's degree spread out.
oh,
over
nice.
years, but I have all like.
Yeah, you have everything you need.
So I think it's gonna be like 1.5 or 2 rather than 4, and it's like, they'll send me, and they pay for me to go to school, they pay for all my stuff and everything, it's at Framingham.
Yeah,
And,
it's right here in town.
yeah, and.
Yeah.
I'll get paid while I'm doing it, and it's like, you go to school for like a semester, and then for a semester you work, and they might send you to a different plant
Yeah,
to like get some experience.
yeah,
And work for, like, in school for a semester.
Yeah.
And you have a semester off where you just work, and it's like, starting off, it's like 61K a year.
that sounds like such a great deal.
And I already went to Michigan State for their.
Nuclear.
year.
You gotta break that habit. Nuclear, there you go.
Summer school,
Yeah, how was that?
it was good, it was very fast paced, it was like kind of short, but
Yeah.
it was really good, and they gave us like a tour of like, the facilities and stuff like that.
Nice. Oh, that sounds so great.
Yeah, and I was able to like, I wasn't with like complete strangers, because like,
Yeah.
there was a guy there that, it was so weird, like, the very first day,
Yeah.
all like get in there, and there's like rows of 4, and then there's one row of just 3, and
Mhm.
on that 3 is me,
Mm-hmm,
this guy named, another guy named Daniel,
mm-hmm,
and then a guy named, I can't remember his name, because it's name was even remember, obviously,
right.
but he goes to Lynchburg.
Mm-hmm. Oh, wow.
Daniel went to June Tech,
Oh,
so it's like just
local
us three in a
people,
row,
yeah.
and we like became friends, and yeah,
that's
that's
fantastic.
sense. Yes. I
Yeah.
was like, oh man, like, where are you from? Oh, he's like, oh, I go to Virginia Tech. I'm like, are you serious? Like, there's only 23 of us here, and you go to Virginia Tech, and the guy's like, oh, I go to Lynchburg. I'm
All
like,
right.
what?
Oh, how is that possible? That's fantastic.
I'm like,
Yes. Yeah, the Central Virginia contingent.
Yes.
Yes. Well, let's start, but that sounds so exciting. You got to keep us posted. All right, so we are going to do an example. So I just want to remind you. The screen's not on. Okay, that would be a helpful thing. Helpful.
Oh, also.
I am. I mean, I don't know if it's gonna work because last time it just didn't start doing its thing. Because it has to convert after whatever. Okay. All right, so we know that in general, we had two formulas for the electric field. And remember, the electric field is a function of R, which is the position out to the field point. Like, where do you want to know the field at, right? That's R. Okay. And it's in general for point charges, it would just be a sum of, I equal 1 to the number of point charges you have, right? K Q I over omega I squared omega I hat. So this is a vector sum, right? And we're going to look at an example of this when we have some point charges. When you have 1 point charge, it's really trivial, right? So if we do an example, we'll do an example with 1 point charge and with 2, okay? And then we had a general form for when we have continuous charge. Oh, just a reminder that K is 1 over 4 pi epsilon naught, right? Okay. And remember that omega, vector omega is, and if I'll put the I on there. And I always forget the order for omega. So I've got to go back. There we go. Would be R, the field point vector, minus R prime 1. The R prime points to the source point. So if you're adding up, the fields due to a bunch of point charges, right? So omega 1 would be, it said 1, I meant R. Yeah, my bad. So omega 1, let's just draw a picture. So let's just say we have a bunch of charges. So we have a charge here. And that's really small, I know, but I don't want to, and we have a charge here. And we have a charge here. Okay, and we want to know the field over here at this point here. Okay, so if I were going to draw all my R vectors, one, I would have an R vector that goes over to the field point. This is not going to change. That R does not change because it's at this point that I want the electric field. Yeah. Okay, so that doesn't change. But then that omega does, well, I'm not done because I've got to write in my R primes. Okay, so I'm just going to look at one of them. I'm going to look at the blue one. Okay, so Q1. So I'm going to draw a vector that goes to the place that Q1 is. This is R prime 1, right? It is the vector that goes to the source that I'm considering. All right, and then the omega is going to go from, oops, let's do it in, what color do we not have? Pink. Sorry, I should have, let me just move this guy. Yellow charge, you're going to move up. Oh, here we go. Q2. And red charge, you need a dot. Okay. All right, so in pink, I'm going to write, and I'm going to move his label to the other side. Okay. So in pink, I'm going to write omega, and that it always points from source to field point. So this is omega 1, right? So in our example here, omega 1 is R, which never changes, minus R prime 1, right? Now, if I went on to the yellow point, I would have a new R prime, right? It would be R prime 2. and it would be a yellow vector going up here. Right, this would be R prime 2. And it would have now a new omega, right? That would point along here towards the field, to the field point, right? Yeah, maybe I should have color coded omega, not pink, but blue. Probably better. Let me just do that for a second because it's bugging me, bugging me. Little OCD coming in. We're gonna show you, you'll see that it depends on the situation, okay? So it depends on the situation. All right, so let's, let me write this now in blue. That makes more sense now. Omega 1, okay? And then in the yellow for, this would be omega 2. Yeah, got it, etc. And then the red would have a separate one, yeah? So let's redo our color coding here. Omega 1. But remember that white R just always stays there, because we're saying, what is the field at the point R from all these charges? Yeah, okay. All right, fine. So if we only had one charge, like say Q1 was the only one, then that's easy, right? So let's say, consider n equal 1, which means we just have a little Q1 there, right? Whoops, sorry. Having my color coding. Q1 only, right? Okay. Then E is easy. E as a function of the vector R is K Q1 over omega 1 squared and then omega 1 hat. Okay. Now, when you would actually calculate this, you need to know things like where is Q1, right? At what X, Y, and Z value is Q1, right? You need to know where it is, right? And where is your field point, right? At what X, Y, Z value is your field point, right? So we'll do an example where we know those things in a second. Okay, so this is for point charges, right? This is point charges. So we'll point charges. Okay. All right, let's look at continuous charges. And here we have a general formula for continuous charges, right? And that is E of R. Remember that field point doesn't change. It's wherever you want the field of. So it's K, 1 over 4 pi. And then it's an integral of dq times omega hat over omega squared. And that dq depends on what situation you're dealing with. Is it a line of charge? Is it a surface of charge? Is it a volume of charge, right? And it depends on the geometry and all, that omega hat depends on the geometry. So we're going to see all this, okay? So we're going to do 2 examples of continuous charge today as well. We'll do a line of charge, and we'll do a much more complicated situation where we have a sphere with uniform charge density, a surface charge density. Okay. All right. But let's go back to just doing some a point charge example, a couple point charge example. Okay, back green. So first, so A, we have point charge at 2, 3, 1. Okay, in other words, X, Y, Z, 2, 3, 1. Okay. And we want the field at 4, 5, 6 or something. Okay, now I don't know if I'm going to go through the whole computation because I'm just made up a really sort of complicated geometry, but I'll show you the setup. All right. So fine, we know that we have a point charge Q, right? So we have Q at 2 in the X direction, 3 in the Y direction, and 1. So let's just put him like right here. Now they can't tell that that's a Z, but it's above the XY plane. So this is Q1. And actually, just to draw it better, I'm going to put him up here. Shouldn't have made it 3D. That was kind of a stupid idea. Anyway, but we'll just go with it. So we know we have an R out to that point. Sorry, an R prime out to that point. I'll use green. This is pointing to the chart. This is R prime. And I'll call it 1, even though we don't have a 2. Okay. And we have a field point, which is at x equal 4, y equal 5, and z equal 6. So let's just put this up here. I know it's probably not right, but like as far as drawing goes, but whatever. Okay, R. Okay, so I know that the field at R is KQ over omega. Let me not call it Q1, okay? I'll just call it Q, sorry. Over omega in the omega hat direction. Okay, so we just got to figure out what is omega. So I know that omega is R minus R prime, right? And so let's see, what is R? Well, it's 4x hat plus 5y hat plus 6z hat, yeah? And R prime, so minus R prime, which is 2x hat plus 3y hat plus z hat, yeah? And then we write down, what is that? Okay, so we have 4 minus 2 in the x hat direction, so we have 2x hat. And 5 minus 3 plus 2y hat. And then we have 6 minus 1 plus 5z hat. Okay, that is the vector omega. All right, let's figure out, oops, sorry, this is squared, guys, the down the bottom, my bad. Okay, so now we need the magnitude. How do we calculate the magnitude of a vector? Yeah, we actually need it squared. Well, yeah, okay, well, I'm gonna do it squared. So it's just 2 squared, which is 4, plus 2 squared, which is 4, plus 5 squared, which is 25. Right? So what is that? That's 8 plus 25, that's 33. Yeah? Okay. And whatever units we're using, which is probably meters, we do meters, right? 33 meters. Okay. Squared. Okay. All right. What about omega hat? How do we get that? That's right. Omega over the magnitude, indeed. So this is going to be 2x hat plus 2y hat plus 5z hat over the square root of 33. And that'll be in meters, right? Yeah. So there we go. You actually know the field now, right? Okay. So we could write that out, and we just write it out finally, and I'll put that in white. So E of R is 2 okay times Q, and then it is 2x hat plus 2y hat plus 5z hat over the magnitude. So notice that this is the magnitude down here, this guy here, and there's a magnitude squared here. So it's really a magnitude cubed, right? So I might as well just write it that way right away. So the magnitude, so it's 33 to the 3/2, right? So there's your electric field. You know exactly what direction it's in, right? Yeah. Does that make sense? Now, the reason this looks a lot more complicated than it did in 116 is that you were always dealing with your charges at the origin, right? Then it was really easy. You didn't have to worry about anything. And you always were doing it in XY plane, not in XYZ. Yeah? Okay. All right. Let's do a more complicated example. where we have two charges. My computer is doing its thing where it's like overheating. Let me just check. Well, we're at 83%. Hopefully it won't drain itself. Okay. All right, we're going to, this is example B. Oops, there should be green in point charge land. So B, so find the electric field a distance Z above the midpoint between two equal charges Q, a distance D apart. Okay, fine. All right, so let's stick this, so let's just draw coordinate system. I don't really care because this thing is, it's in a plane. Now, so think about it, right? There's two charges like this. No matter how they're oriented in space, I can define a plane in which they're in. I could also have done that for the previous problem and it wouldn't look so ugly, but why bother? But, right? Like I could move my origin. I could have moved my origin to where that point charge was, right? But if I have more than one point charge, then I have to make some decisions. But anyway, so here I have 2 point charges. I'm just going to choose to be in a plane so that the on the y-axis lies along the 2 charges. So let's put them down. We'll have Q1. They're both the same magnitude. Actually, let me move this down because we're going to take a little room. Q1, and we'll have Q2, and the y-axis will be between them, like this. And then we'll have the z-axis going right from the middle up. Hope you agree that I can move my coordinate system around to just match up with where these things are in space, right? Okay. All right. Fine. So I put it in the middle. So this means that this distance here is d over 2. And this distance is d over 2, right? And I'm putting a point here at a distance z above that I want that's gonna be my field point, right? That's where I want the field. All right, now often when you do problems like this, you need to think about symmetry. So we're gonna think about symmetry here and think about what the electric field might look like, right? Before we really do that much work. Yeah. So let's think about the electric field. This guy over here, you should think of as, so let's just say this is a positive charge for a second, Q. We don't know what it is yet, it doesn't matter. What happens to a test charge, a positive test charge that's here? Which way do you think that this Q will push this test charge if it was here? Just up the Z?
Oh, no, it's gonna be an angle, it's good.
That's right. That's right. So you're gonna have a force in this direction, right? So this is how you think of the direction of the field. You think of which direction would a positive test charge be pushed? Okay, you're not calculating forces, but that's what you think of, okay? Which direction would a positive test charge be pushed? Okay, so this would be E due to 1. What about for, so let me color code E, 1 to be yellow. Okay. It's the same on the other side, so let's color code him to be pink. All right, so it's going to be like this. Right? Okay, because we were told they were equal in magnitude, right? Or equal charges. So if both of them are negative, we'll think about some other thing, but like it doesn't matter. You'll see. All right, so do you think there's a component of the pink and the yellow that might cancel out? The one along the Y is gonna cancel. So we don't need to worry about any kind of Y components here. We know that it's all gonna add up along the Z. The Z components will add up, but the Y components are gonna cancel. Right? So we don't have to worry. All right, but let's keep going. So we're gonna have an omega 1 in yellow going from the source to the field point. This is omega 1. And we're gonna have an omega 2 that goes from the source to the field point from Q2. So this is omega 2. And then we have two R primes, right? And they go from the origin of our coordinate system to the source itself. So I have a yellow R prime for R prime 1. And I have a pink R prime for source 2. Yeah. Okay, cool. So not too bad. And then this distance here in green is Z. They said, you know, a distance Z above the, right? That's the Z axis, but the actual distance between the origin and the point is Z, right? Okay, so we just need now to calculate. We know that we just need to add up the two electric fields and that we don't care about the Y components. So the vector part that's Y, we don't care, right? We just don't care. All right, I'm going to define an angle as well because it just makes life a little easier. And they'll be equal angles, but let's say I'll put a little phi here. It's a little tiny. And it's the same here, phi, right? Okay, so that'll help with us. But let's write down, let's just look at the electric field due to the yellow charge. E1 is equal to K Q1, which is just Q, so I'll just leave it Q. Omega 1 hat over omega 1 squared. Okay, well, let's figure out the easy one. What is omega 1 squared? What do you think? With the right triangle. What is the magnitude squared? Think back to high school geometry. Maybe we should do a little bit more work. Let's tiny bit more work. Let's just remind ourselves that my bad, yellow, that R1, right, is just D over 2 in magnitude and in the negative X, Y hat direction, right? R prime 1, R prime 1, sorry, R prime 1. Yeah, maybe that'll help. High school geometry. Theorem starts with a P. Yeah. So what would what's the omega 1 squared? Z squared? Well, right, but what is R prime 1? You don't need the Y hat, remember? It's Pythagorean theorem, right? Okay, yeah, so we got that done. All right, perfect. Okay, omega hat, we could do what we did before, but we actually need like a vector direction here. We don't have that yet, right? We could think about what is omega, what is the well, okay, let's do this. Let's write down omega 1. Okay, well, I have that phi there, right? So omega 1 is going to be the length of omega 1 times the cosine of phi, right? Yeah. Okay. And that's in the x hat direction, right? And then plus omega 2, omega 1 sine of phi. Ooh, why did I say x hat? I mean y hat direction, right? It's in the positive y hat direction. Yes? Just notice how it's leaning over this way. You got it? And then plus sine phi, and up, and it's an upward pointing, times the z in the z hat. Remember, we do not care about the y hat directions of anything here, right? So this means that omega hat 1 being omega 1 over omega is, right, is just going to be cosine phi y hat plus sine phi z hat. Okay, again, I don't care about the y, so I'm going to ignore them in a minute, right? I'm just going to be like, I don't care about you. So, all right, so I think I can write down my E1 now, right? E1 is KQ. Sorry, I gotta do a better Q there. Q, and then omega 1 hat, which is cosine phi. Oops, sorry. I don't care about the y components, right? Sine phi z hat over z squared plus d over 2 squared. Okay, but I don't really want that sine of phi anywhere, right? So I got to figure out what is that. Well, that's easy. What's the sine of phi? It's just the opposite over hypotenuse, right? So sine of phi, let me write it down here. Sine of phi is just the z over the length of omega 1. Okay, so that's easy because I have an omega 1 squared down here, right? This is omega 1 squared. And so if I add another omega, remember that's the square root of this stuff, right? So I'll get to 3/2 again, right? And I'll get a z. So I'll get k, q, z, z hat over z squared plus d over 2 squared, all to the 3/2. Okay, that's E1. What do you think E2 is? Yup, it's the same, right? So really, the field, right, that's E1, the total field, E, let's write that in white. E is, and it's a function of z now, right? How far away you are, is going to be 2 times k u z in the z hat direction over omega cubed. So I won't write that out, but omega, remember, the magnitude of omega is the square root of z squared plus b over 2 squared, right? Does it make sense to you? Yeah. All right. Cool. All right, so that's how you apply it to just 2-point charges. You can see it's, it's a little bit of work and you have to really think vectorially. Yeah. And the better you get at that, the easier this will become. All right, let's go on to, let's see what we're doing on time. Looking good. All right. And let's move on to a line of charge. So this will be our first example of a continuous charge distribution. Let me check the computer if it's about to die. See, it's like, it's plugged in and it's losing power. Let me just real quick, I'm going to do that, what I did before, try to get so see what's using all the power. What's it called? Shoot, I forgot what it's called. Thank you, I always forget. Hello? Yeah, there we go. All right, CPU. Zoom is using a lot of stuff. What else? I can't see. Oh, Windows server. Okay, whatever. I can't do anything about Zoom.
Because I'm talking to Noah, and Noah said that when you were over the summer for like classes.
Yeah. Yeah, it's probably true. Yeah. My computer's just having issues. It needs to be rebooted from, it's not in good shape and it's relatively new.
I'm just in a poetry class, it's in this class.
I know. Yeah, he's the one that told me that that wasn't kind of vandalism. It was like the teacher saying, do it. She's like, really? Dude, like I said, okay. All right. So let's do line of charge. So let's see, what was our color coding for that? Yellow. It's a bad choice, but whatever. All right. So example A, we're gonna have a line. Oops, I meant to do yellow, but line of charge. And we're interested in a distance above the charge. Okay, we want to know like above the charge, like what it's an infinite line of charge, by the way. So okay. So we just want to know what is the field above that line of charge, some distance away. Okay. So let's set up the problem. So we're going to have the line of charge here, it's represented by that. We're going to have a field point up here. And so I'm going to put my coordinate system right here and just start by drawing out the vectors, right? So I have the R vector going straight up. And then now I have to think a little bit. So I'm going to call this, I'm going to lie my line of charge along the x-axis, okay? Just so I can have a little coordinate system. And then above the coordinate system, so I've called it Y before. If you prefer, I can call it Y. Maybe that's less confusing. Let's call it Y because I am going to call it Z above. So we have a coordinate system that looks like this, Y and Z. Okay, just like before. Okay. All right, fine. But now when we are looking at R prime out to a source, it's no longer a stationary source out at D over 2, right? We have to point all along the line to a little bit of charge somewhere, right? So I might have to go, I'm going to just draw one out here. So let's say here's a little bit of charge, little dq. And dq is going to be lambda dy, right? Because it's proportional. So remember that lambda is a linear charge density, line of charge. I forgot to put linear charge density. Lambda is in coulombs per meter. And I should have said, this is a line of with a constant charge density, right? I should have said, hey, this is a constant charge density. So this lambda does not depend on Y. So if I move in Y, my amount of charge does not change. Now you certainly could have a line that has a changing lambda, but we're just gonna let it be constant everywhere on that line. Does that make sense? So if I take a full meter of my line of charge, I get, and let's say lambda is 2 coulombs per meter, I'll get 2 coulombs worth of charge in that 1 meter, right? Okay, but it's constant everywhere, so I'm not going to worry. But certainly someone could have said, hey, lambda is, lambda of Y, and it's, Y squared plus 2 or something, whatever. All right, but in this case, it's constant. Okay, all right. So let's, let me see, did I make it? I have to remember if I made it. No, I'm sorry, I did not make it infinite. So it has a length, this charge. Should have set it up right. Okay. Length L, line has length L. And just like before, we're sitting in the middle, right? We're looking up above the middle of the charge. I should have written down the formulation of the problem a little bit better than that. Okay. All right. So we have a little dq. And I know that dq is lambda dy. But when I want to point out to it, right, with my R prime, that's what I'll do. I'll write an R prime that looks like this. It's pointing to the little dq, right? That's what it's always going to do. So this is R prime pointing to the little dq. And of course, there's also a omega pointing from the little dq to the field point. Okay, now that is good. Imagine now that dq, we have to add up all the dq's on one side and all the dq's on the other. So if I'm putting my origin here, then this would be minus L and this would be L, right? So we're half of the lines on the one side and half of the lines on the other. That makes sense? Okay, so now I've got to add up all those little things when I do this. So I'm gonna have to do an integral. All right, fine, we knew that. Let's keep setting stuff up. So R prime, let's set up the vector R prime. R prime, well, it's just going to be Y in the negative Y hat direction. Right? It's how far are you out? Right? That's its length. And it's in the negative Y hat direction. Okay, what about R? R is just Z, how far up you are, right? In the Z hat direction. So we're just saying let it be up at Z. That's really what we're saying, right? Now, when you're done, you should have a function of Z, just like we did before, right? We had a function of Z. We weren't saying let Z be 2. It could be anything. And so you would go and calculate if you needed your field at 4 meters above the above this 2-point charges or 20 meters, right? You could calculate that. Sorry, let me get a tissue. My nose is about to run. I know, right? All right, what about omega? Well, that's easy, right? Because we know that omega is R minus R prime, which makes it really easy, right? It's Z hat minus Y or plus Y hat. I probably should have set this up so we were going in the positive Y direction and first, but instead of this, but okay. Right, I should have put my DX, my DY on the other side. Whatever, okay. All right. Oh, yeah, okay. Right. It would have just changed the sign on omega. Never mind. It's no big deal. All right. Fine. Now, again, we have a symmetry thing going on here, right? Don't we? There's as much line on the right as there is on the left. So the field that's pointing along the Y direction is going to cancel for every. So think about 2 DQs, one here and one equidistant over here. It's going to cancel. One be pushing this way. One's pushing this way, and so the Y components cancel. So we're just interested in Z components anyway. Not too worried, right? All right, let's calculate the length of omega. I'll do it squared. It's of course Z squared plus Y squared. Yes. Okay. All right. And we know what omega hat is as well. Let me move my picture. My picture is like, okay, so we have omega hat is omega vector over omega. So this is going to be Z hat plus Y hat. Again, I'm going to ignore the Y components in a second, but I'm not there yet. Over Z squared plus Y squared to the 1/2. Yeah. All right, I think we have all of our pieces that we need, right? We have all the pieces we need. All right, let's see. Let's now remember what the integral looks like, right? So the integral for E looks like, and it's going to be a function of Z now, right? It looks like the integral dq, well, I'm sorry. Hey, we have K. K dq omega hat over omega squared. And in this case, right, we have K, a linear integral. It's not, because we don't have a line of charge. This is going to be lambda dy, right? And now I have omega hat, which is Z hat plus Y hat. And I have Z squared plus Y squared. So the 3 halves again, because I had a squared, right? I have a squared one here, and I have one in here that comes, right? Does that make sense to you? Okay. We keep doing the 3 halves. You'll see it's like always like that. Okay. Now, this integral I just wrote down, I gotta be careful because this is really negative L to L. I mean, negative L to 0, right? Because this sign right here is positive. Now, if I went to the other side, that was gonna be negative. That's why they cancel out. But you know what? I don't care because I'm just gonna get rid of those y components altogether now, right? That makes sense? Okay, so I'm gonna get, this is gonna be K. I can bring lambda out too. That's just a constant. And now I'm going to go from negative L to L, right? And I'm going to have dy times z. Oh, z can come out too. I'm not integrating over z. Can you come out, z? And then over z squared plus y squared to the 3 halves. Yeah? And this is all in the z hat direction. Yeah? Okay. So, you know, you can go look that integral up. That's easy to look up because z is just constant, right? And it's just basically something plus y squared dy all to the 3 halves. And that's easy integral to look up. Or if you know how to do those integrals and feel yourself, you know, feel free. All right. But let me just write down the answer. I'm going to go to a new layer. And I'm going to erase all this so we have a little room. Let me fix my eraser while I'm sitting because I'm just going to drive me nuts. So I gotta fix it. Brush palettes. Okay. To chisel tip. Yeah. Okay, so that's better. I didn't. It's still chisel tip. I just changed the size of the eraser. Yeah. All right, so this is going to be K lambda Z and then Y. This is the integral now. I just did the integral. Z squared on the bottom, square root of Z, my bad, not 2, Z squared plus Y squared. And then from negative L to L, and we still have our Z hat because it's a vector, right? Okay, and then equals K lambda over Z, and then L over square root of Z squared plus L squared plus L over Z squared. So I'm just applying the limits, Z squared plus L squared, and then times Z hat again. And then this gives us, again, 2 K L lambda L over Z, and then 1 over Z squared plus L squared in the Z hat direction. Final field answer. Okay. So let's look at a limit of this. Let's look at what happens when you're super far away, when Z is a lot bigger than L. So now you're zoomed way out. You're way above this line of charge, right? Way above the line of charge. Let's see what happens. So I'm going to get a new layer and erase all the calculations. Okay, and then we'll just write down the field again. Well, it's down here. All right, so let's look at Z a lot greater than L. So you're just like really far away from it. Okay. All right, so now E is equal to so this means that 1 is a lot greater than L over Z, right? Okay, so what I'm going to try to do in my E is I'm going to, and I shouldn't have erased all of the E, so let me just put it back. E of Z equals 2. Okay. I'm going to try to write everything as L over Z, okay? Okay, fine. So that's pretty simple. So we're going to do 2 K lambda L over Z. So I have an L over Z there. And then I'm gonna pull out a z out of, from here. Pull out a z squared. Yeah, and so I'll get one, well, I'll put z hat over, z comes out, and I get square root of 1 plus L over z squared, right? Which is now approximately, this thing is so small compared to 1, right? That I don't care about it, right? So this just becomes 2k lambda L over z squared in the z hat direction. Okay, let's think about what this is. So this is so let's think about what is lambda L. Well, actually, so tell me what is physically, what is 2 lambda L? What's 2 lambda L? Remember, this thing is 2L long, isn't it? Because we stuck it in the middle, and there was an L on one side and more L on the other side, like this, the same L on the other side. So it's 2L long. So what is 2 lambda L?
So
Yeah, lambdas and coulombs per meter,
it's 2 times Q.
not 2 times Q. The whole thing is 2L long. So let's say lambda was two coulombs per meter. And my L is 1 meter. The whole thing's 2 meters long. So when I multiply 2L times lambda, what do I get back? Let lambda equal 2 coulombs, 2C per meter. And let L equal 1 meter. Right? But the whole line is 2L long, isn't it? No, this is not the charge density. What do you get when you multiply 2 times lambda times L? For what though? And what does that represent? The charge density? No. The total charge of the whole line. Right? Okay. So this really is the total charge K Q over Z squared in the Z hat direction. What you would expect from a point charge with total charge Q. Z away from it. Right? Isn't that true? Isn't that the formula for a point charge, really? Except for it's not R, we're just calling it Z. Yeah? Yes. So that should make sense because we're far away from it. It's a little tiny line. Yeah. Make sense, sort of?
Yeah. So if we zoom out far enough,
It acts like a point charge. You far enough.
if we would zoom in on it, what?
Well, it's a line.
Well, it's a line, but like, I mean, in this, if you consider a point charge, if you would have zoomed way in on that point charge. it's not-
Well, no, and so in physics, true point charges are actual points.
Okay, so that's.
Kind of, yeah, like think of it as an electron. You can't subdivide an electron.
Got
Right? Okay. All right, so good. Let's see what time it is. Ooh. I wanted to do one more example, but it is a little hairy. It's hairy. We can do it. I just don't know if we're gonna finish it, but it'll be quick to finish when we come back anyway on Monday. By the way, the first test is next Friday. Aye. Okay. Yes, we do. Yes, we do. In terms of time. All right, let's do it. Oh, what was that? Something, oh, for crying out loud. No. you know, might make it through the rest of the lecture. Huh? What do you mean, what's it on? Let's see. 57. It went from 85 to 57 during this lecture. No, 100. It went from 100 to 57 so far. 20 minutes. Hope so. Okay. I'm gonna put up a picture for this one because it's so. Let's see, is this the right screenshot? Yeah. It's gonna be hairy. Indeed. Okay. So we'll write on this layer. Okay. So yeah. All right. So here's the setup. The setup is we have a sphere with surface charge, constant surface charge, constant sigma. Okay. Constant surface charge on the surface, obviously sigma. And we're looking for the field at that point, the big black dot on the z-axis above the sphere. So the sphere has got charge smeared uniformly around its surface. And then we're looking for the field, you know, some distance above it. So I just orient the coordinate system so that the origin's at the center and z is along this line that I want to calculate. But I hope you know that I could rotate that coordinate system anywhere, right? And you get the same answer by symmetry. Okay. So, all right. So remember that we know that the integral that E is equal to K times the integral of dq omega hat over omega squared, as we know. And dq this time, why did I put dg? I don't know. dq is equal to sigma dA, right? Because sigma now is a surface charge density. So sigma is a constant, but it is coulombs per meter squared. Yeah. So if you had a little patch on the sphere of area 2 meters squared, right? Then your charge in that patch would multiply sigma times 2 meters squared. And you got the coulombs, the amount of charge in the little patch. Yeah. And the total charge, you'd have to integrate up. You'd have to, well, it's a constant charge density. So that means that the total charge is just going to be sigma times the surface area of the sphere. The sphere has a radius big R. Yeah. Okay. So, all right, but it's constant. Again, we could have sigma that depends on R, theta, and phi. Like if you move around on the sphere, sigma could be a different charge density, right? But it's not, luckily. Okay. Okay, fine. So what is dA? Well, we're going to use spherical coordinates, sort of. We're going to have a mix, you'll see. So sigma, so in spherical coordinates here for dA, remember that on the surface of the sphere, R is not changing, right? So our dA is going to be our dL theta times dL phi here, right? Because those are the only two things that are changing. And if you recall, this was going to give us sigma times the radius squared times sine theta, d theta, d phi. Okay, there we go. That's dq. All right, now we got to put together all those other pieces, right? All right, so notice we are pointing out here, right, to a patch on the sphere right here, okay, given by dA, right? Okay, so we're pointing out to dA here. Can you see my cursor, right? Oh, you can't really see it too well. So if I point out from the origin, right, that is my R prime because it's pointing from the origin to the source, dA, to a little patch. Well, the magnitude of my R prime is always big R because I'm always going to the surface of the sphere from the origin. I put the origin of the coordinates in the middle of the sphere, which would only make sense, I hope, right? For what you should do. Okay. Okay, fine. So we still have to get all the other things. So up here, remember, this is that script R, which is our omega, right? This guy here. And this would be R, which is just going to be in Z hat direction. So, right, if we think about what is R, let's do that in yellow, you can see it. Can you see the yellow coming up on that line? Yeah, and so R, it's just going to be Z hat, right? Always. Okay. R prime is just R, but then it has some random direction. We'll deal with that later. And this guy we have to calculate. Okay, fine. As far as the length of omega goes, right? That's a little easier than getting the vector version of omega, which I'll do in a second. But let's just get the length. So I know it's hard to tell, but if you look at that triangle that's made by R prime, and omega, right? It's not a right triangle. So what do we know that allows us to get the side lengths when you don't have a right triangle? Law of cosines. Like, that's true, but you need two angles for law of sines, right? You need two. We don't have two. So we got one. We got theta, right? Okay, good. So we have law of cosines to write down omega. So omega. Okay, so omega length squared is law of sines, which tells me it's R squared plus Z squared, right? So it's the length of R prime squared, the length of R squared, which is Z, minus 2RZ cosine of theta. Okay, well, we got that. That's good. That's good. Okay. Fine. Fine. Now I need, so I've got that. Now I need omega hat. Okay, so let's think about what omega hat is. All right, well, so think of it this way, right? You have, if I draw kind of, like, think about the direction of omega hat. This is omega coming up over here in the orange. I don't know if you can tell it's orange. But yeah, it's orange. It's not very distinguishable from pink, I'm sorry. But if I come up here, this is omega hat. And it has the same angle, this side. Yeah. So I can write that and then let's think about symmetry wise. Let's think about what we care about. So now let's imagine that patch, right? That omega hat that I just draw is the direction of the electric field from that patch. Now imagine moving that patch, but only moving it as if you were taking sort of a great circle around the whole sphere like this. All of the points that aren't on Z will cancel, right? So I only care about the Z component. And that's going to be true if I move the patch down to this great circle or any other great circle. I don't care because they're going to cancel. And so I just have Z. Okay, so that's cool. I can calculate the Z component of omega hat. That's easy. So Z is going to just be cosine of this angle times Z hat, right? Yeah, you agree with that? Yeah. Cool. So that's going to be cosine of this guy, Z hat. Now, the deal is I've got to get that cosine of psi. Okay, here's where this figure comes in. And I think what I'm going to do is turn off this layer for a second so you can see this unadulterated. And I want you to, and I'm actually going to copy it so we have another one to write on, and we still have a clean one. So I'm going to go to a color you can probably see better. All right, so let's take a look here. So psi, right? I want psi, I want the cosine of psi. All right, now look at the right triangle that they've drawn on this this diagram for you here. That is omega on one on the hypotenuse, right? So this is omega on the hypotenuse, z, and whatever this is, which I don't care. Okay. All right. So, but oh, sorry, it's not z. My bad. My bad. Z is this entire, but I'm not writing here in red. Z is this entire thing. So what I need to do is subtract out this bit, right? And this bit is just our cosine theta. Yeah. So if I want, let's say the cosine of phi, why did I say phi? I mean psi, cosine of psi, right? It's this length here, z minus this, so it's this length here, right? The adjacent, z minus our cosine theta over the length of omega, right? Yeah, you buy it? Great, cool. All right, so let's go back, turn that off, and go back here, turn that back on. All right, so now we know that this is, because I need this to be orange, so this is going to be z minus cosine theta over omega in the z hat direction. Yeah? Now we're ready to put it all together. It's nasty. We can put it all together. What time is it? We have 9 minutes. So you might not be able to do anything but just put it together. Okay. The morning, it's going to be nasty looking. All right, so I am going to get rid of all our drawings. We get a new list. All right, so finally, we are ready to put together E. Now remember, it's just the Z component because we don't care about the other components at all. Okay. It's going to be K. And here we go. We know it's going to be the integral of sigma dA. So sigma r squared sine theta d theta d phi. And remember this, that integral there you see is actually 2 integrals, but I'm not drawing it out yet. And then it's going to be omega hat, which is z minus r cosine theta z hat. Oh, actually, let me not do that. I'm not putting the z on the e, okay? Because I'm keeping the vectorial nature. And then remember there was a 1 over omega from the z from the hat, right? And then there was then there was omega squared on the bottom. And remember what omega was? It was r squared plus z squared minus 2rz cosine theta, and now everything's to 3/2 because I had 3 factors of a half, right? I have 3 of those now. Again, right? Okay, this is ugly. It's ugly as crap, right? Ugly, ugly, ugly. And remember, it's 2 integrals. Now, I can do one of the integrals right away because there's an integral of a d phi from 0 to 2 pi. That just goes around the sphere. And there's no phi's anywhere. So I can easily remember that the integral of d phi from 0 to 2 pi, of course, is just 2 pi. So I'll bring out a 2 pi. So I have k times 2 pi, and then I have the integral from, 0 to pi of theta, right? Oh, let me bring out all the constant things that I don't need. How about that? So r squared is constant. Yeah, that's it, really. Okay, so, and then I have the integral from 0 to pi of, oh, sigma's constant, of sine theta z minus r cosine theta. And then I'll put the z hat up here. And over r squared plus z squared minus 2rz cosine theta to the 3/2. Yeah, and this is all integrated d theta. That's ugly. Okay. I am just going to, there's a u substitution you can do where you do u equal cosine theta. And that makes your life just slightly better, so I'll just write that down. Keep track of time for me, would you? U equal cosine theta, du equal negative sine theta d theta. Okay. So if I do that, I get E equal K times 2 pi times sigma times R squared. And then, yeah, that's it, I think. And then I get from -1 to 1, Z minus RU over R squared plus Z squared minus 2RZU to the 3/2. And this is all DU. Okay. And we, of course, would just look that up. Right? And we end up with 2 pi. Actually, let me just go. Are you guys okay to go to a new layer? I'm just gonna write down the answer. Okay. So after looking that up and applying the limits, you get E is equal to K 2 pi R squared sigma over Z squared. And then Z minus R over the absolute value of Z minus R minus, or no, plus, sorry, plus Z plus R over the absolute value of Z plus R. Boy, that's ugly, huh? Super ugly. Okay. And we'll come back to this right at the end of the next class, or beginning of the next class, sorry, my bad, beginning. And this is a lead in to Gauss's law, which we're going to be studying in the next part. Okay? Because we're going to see that this nasty thing was completely unnecessary. All right, let me turn this off and see if it's going to start converting or not. Stop share. Come on, Zoom. And where's the stop recording? Okay, stop.